haven't been working with Azure for a long time, you should know that storage was a very big initial pain point, because at the beginning, around 2012, 2013, we first got VMs. We had no capacity for shared storage, or for SSD storage. It was all slow spinning disk, and storage latency was a big issue. So in this talk, we're going to talk about a couple of things. We're going to talk about SQL Server's internals and how SQL Server does stuff. And I think that's really important to have a fundamental understanding of, because there are factors you can control, like adding memory to a VM, that may impact positively or the way your storage appears. It's also really important to understand your database workloads, because one of the things that can masquerade as an IO problem, like where you're seeing really high latency numbers, could just be because you're completely overwhelming the subsystem because your queries are suboptimal or your indexing strategy is also suboptimal. So it's helpful to understand those things. And remember, you're looking at kind of a holistic view. I have a pretty cool demo plan. We're going to kind of talk through it from the Azure side. We'll look at metrics, and we'll also look at running real workloads versus synthetic workloads, which are how we typically test a disk. So like Michelle mentioned, I'm Joey D'Antoni. I'm principal consultant at Denny Cherry and Associates Consulting. I'm a data platform MVP and a VMware expert. I blog at joeydantoni.com, and I don't have my Twitter handle on here, but it's at jdanton, and you can hit me up after this if you have any questions that we don't get answered during this session. So as I said, we're gonna kind of walk through SQL Server usage patterns. We'll talk through, the way writes happen, the way reads happen, and this is some kind of deep internal stuff. So if you're not deeply familiar with SQL Server, remember a SQL Server database is broken up into a database file and a transaction log file. You can have multiple of both of those, but you would only ever want one transaction log file in most scenarios. But we'll walk through that architecture of how SQL Server performs I/O, because that's really what we want to understand to design a proper storage subsystem. We're going to talk about Azure Storage, and there's a lot of aspects for Azure Storage. I could probably teach a full day class on all the scope of Azure Storage, if not possibly multiple days. But we're going to focus on storage as it affects VMs, and then specifically as it affects SQL Server workloads. And I've had the good fortune to have some very large clients where I was able to do a great deal of testing to understand the different characteristics of the different types of Azure disk and in those workloads that are available to you. So one of the things I like to walk through is the way SQL Server just does things. So this can be kind of widely misunderstood, and we'll walk through the details of this. But writes to tables take place in memory and then are later cascaded to disk for data files. I should have added some clarification there because I think I have a little bit of confusion. Writes to the transaction log happen indirectly, but nearly directly. There is a transaction log buffer that SQL Server writes to. And actually, let's take a step back and talk about buffers, because if you lack some understanding around that, it will be helpful to understand. One of the ways databases have always been built was with the notion that going to disk was very expensive, and we should minimize the amount of round trips to disk that we have to make. So in doing so, databases pretty aggressively use buffering, and that means areas of memory that we like to refer to as a cache, where we can either read or write from, so we don't have to go to disk locally. And we're going to talk about several layers of caching, especially when you get into Azure Storage. But the main thing to remember is, even if you have ultra-fast NVMe storage, the kind that powers UltraDisk in Azure, it's still orders of magnitude more expensive to make a round trip to that storage than it is to read from memory, because the memory is very physically co-located near your CPU. And if we think about storage in Azure, it's inherently networked. So that also means that you're making a network round trip. A lot of, in some cases on-prem, you'll have directly attached storage, and we'll talk about some directly attached storage in Azure. But in general, it's remote storage, as if it were in a SAN, except you're going over an Ethernet connection in Azure, as opposed to when you would probably be a fiber channel connection on-prem, which tends to be a little bit lower latency and higher throughput. So you want to minimize those round trips. And the way databases preserve data integrity is by writing directly to the transaction log. So even though your writes take place in memory to the table, so if you insert new records into a table, that the pages for that table are updated in memory, the fact that you wrote those values are what gets written to the transaction log, and that happens directly so that the transaction can be committed. It does flow through a buffer to lower the burden to disk, but it's still that transaction log can be a limiter of your performance, especially if you're under if you're doing a very heavy insert workload. So if you're inserting a ton of records, you can see a wait type from SQL Server called write log, which will indicate that it's waiting to write to the transaction log. The other thing we do is have checkpoints, and checkpoints are one way we write data to disk. We'll talk about some others in a few slides, but checkpoints allow you to allow SQL Server to take those pages that are in the buffer cache that we've inserted and mark them dirty, or that are marked dirty, which means they've been updated. It will then flush those pages to disk into your data file, and that's how SQL Server preserves integrity. In general, if you don't have a lot of experience with SQL Server, just remember databases inherently are high I/O applications unless they're idle. But under normal utilization, databases perform a lot of I/O, whether it's reading, inserting, they're heavy I/O activities. So they're big consumers of disk. And the other thing too, a database server will always like more memory. So this is kind of an internal thing, and I always like to talk about this stuff, and it may be, if it's above your level, don't worry, we'll walk through it. So what happens when a user issues a query? So we have our user starting at the top right here. This would be our computer that's issuing the query. It makes a connection to SQL Server over TDS, and then that command gets parsed by SQL Server. All the parser simply does is says, is this a valid command? And what objects do I need? So it's checking for the existence of the tables and columns in the statement. That gets passed to a feature of the engine called the query optimizer. The query optimizer then generates a plan, and that plan is how SQL is going to retrieve that data. It may bypass creating a plan if there's a plan that exists. This is another place database engine uses cache. So if you've run this query before or recently, and everything is still valid about the data, it will go straight to the query executor. And this is where we get interesting. So we go down to access managers, and depending on whether this is a read statement or a write statement, we may just go to the buffer manager and get cache pages from the buffer pool. So we have the buffer pool right here. If the pages are in cache, SQL Server will get them. If they're not in cache, it will go to the physical disk and write and read them. For write methods, SQL Server will then perform a transaction and write to the transaction log, and then eventually write back to the buffer pool, or write to the buffer pool and then write to the transaction log. Eventually that IO will be cached back. So these are all the kind of internal components to the database engine that allow you to perform, allow SQL Server to perform consistent IO in a way that performs pretty effectively. So using all of these various buffers, even though it increases the complexity of the code, it greatly increases the performance of the product. So let's walk through an update. So if we have a simple kind of update statement, and this isn't a real table, I just made an example. We're updating our customer table for customer X, setting zip code equal to 98052. You'll also note I didn't put a where clause in this update. Don't do that. So if you're doing this, let's assume we have a single row in this table right now. SQL Server will locate the table and row with that record, and then the 8K page containing the record. So remember, SQL Server stores data in 8K pages. Those pages are formed into a 64K extents, and that's typically how SQL Server reads data from disk. But when that page is modified in the buffer cache, it is not immediately written back to disk, as I mentioned. What happens is the page is marked as dirty, and that means a page can have more than one logical write made before it's physically written to disk. For each logical write, a transaction log record is created in the log cache that records the modification. Those log records, they have to be written to disk before the dirty page is written is removed from the buffer cache and written to disk. So SQL Server uses a technique known as write-ahead logging that prevents writing a dirty page before the associated log record is written to disk. This is a very kind of a quintessential part of how SQL Server works. When that buffer manager writes a page, it also searches for adjacent dirty pages that it can gather in a single write operation. So the overhead of doing a write is high, so SQL Server can write multiple pages at the same time. That's beneficial. So adjacent pages have consecutive page IDs, so each page has its own ID and are from the same file. The pages don't have to be contiguous in memory, they just have to be contiguous on disk. The search continues forward and backwards until either a clean page has been found, 32 pages have been found, or a dirty page whose log sequence number has not yet been flushed into the log. A page that is found can be immediately lashed, so it's locked in place effectively. And in this way, SQL writes a group of pages to disk in a single write operation. Just before a page is written, the form of page protection specified in the database is added to the page. This is where SQL Server takes a checksum. The page is marked with an update latch, and it writes that checksum to the page. And then finally, the process is complete. But what makes our transactions complete here is when the page gets written to the log, and that marks the transaction as complete. So that's what we need to happen relatively quickly. There's a few processes as to how SQL Server does does writing to the data files that are kind of interesting, and lazy writing is one of those. So the lazy writer is a system process that keeps free buffer space available by removing pages that aren't used very frequently from the buffer cache. Because remember, that buffer cache is considered to be pretty valuable space. We don't want to waste it on things we're not using all the time. So dirty pages are first written to disk with the lazy writer. Eager writing writes dirty pages associated with some non-logged operations. SQL Server does have operations that aren't logged, like bulk insert and select into. Those are things that you're trying to optimize the write speed of, and you can avoid, they're not granularly recovered. That process allows creating and writing new pages to take place in parallel. And so eager writing doesn't have to wait until the entire operation finishes before writing pages to disk because it's non-logged. Finally, checkpointing. The checkpoint process periodically scans the buffer cache with pages from a specified database and writes all of those dirty pages to disk. This can be a very, very IO intensive operation. So frequent checkpointing can be problematic. Not that it's something you have control over. Really, the way to control it is to add more memory. But checkpoints save time during later recovery by creating a point at which all dirty pages have been guaranteed to be written to disk. And the element of this, and some of this kind of changes with SQL Server 2019, that data is written to the transaction log first, because in the event that SQL Server crashed, on startup, it's going to read that transaction log and perform recovery of all the transactions that are not in the data files. This whole architecture changed with a feature in SQL 2019 called Advanced Data Recovery, with the way Microsoft manages that data. But prior to that, it could take a very long time to come back up if you hadn't checkpointed. So hence checkpointing somewhat frequently based on the amount of log space used and the time elapsed since the last checkpoint. You can also manually force a checkpoint by issuing the command checkpoint, or other activities will trigger a checkpoint, like if a data or log file is added or removed from the database, or if SQL Server is stopped. All three of these processes do not wait for the IO operation to complete. They always use either asynchronous or overlapped IO and continue with other work, checking for success later. So this allows SQL Server to maximize both CPU and resources and IO resources for appropriate tasks. One other thing to note, SQL Server will reduce its write rate when latency reaches 20 milliseconds. 20 milliseconds is kind of a good threshold for good versus bad IO performance, and we'll walk through some of those numbers when I'm doing a demo. But in an ideal high performance system, I would never want to see, especially write IO, above 20 milliseconds. I consider that to be pretty high. Ideally, you want to see single digits. In general, taking back and looking at a larger viewpoint, 50 is a more common threshold for average systems that aren't supporting kind of mission critical workloads that demand high I/O. And if you see anything that's in the triple digits, it's usually not going to be a good experience. SQL Server also does some interesting reads. So we talk about 8K pages, and a lot of people think SQL Server reads in 8K or even 64K with extents, and that's not always the case. I/O from an instance of SQL includes both logical and physical reads. And the difference between logical and physical reads is that a logical read is what happens when SQL Server reads data from the buffer cache. If the page is not in the buffer cache, a physical read will copy the data from disk into that cache. And those read requests are controlled by an internal component called the storage engine, and as well as the relational engine. So the relational engine is what generates the access method, like a table scan or an index seek. And the access methods and buffer manager components of the storage engine perform those operations, and then the storage engine will also try to optimize those things. One of the ways the engine optimizes this thing is called read ahead. So read ahead assumes that if you're reading a page, that you're probably going to read the next few pages or even more right away. So it anticipates the data and index pages needed for an execution plan and brings those pages into the buffer cache before they're actually used for the query. This allows for computation and reading the data to overlap, so you're taking both full advantage of the CPU and the disk. SQL Server can read up to 64 pages from one file as long as they're contiguous. And this read is performed as a single operation to gather the number of buffers into the buffer cache. If any of the pages in the range were already in the buffer cache, that corresponding page will be discarded when the read completes. And that range of pages may be trimmed if any other pages are present in the cache. SQL Server will do read ahead on both data and index pages. And one of the things to note is that table scans are used to read data pages, and they're very efficient. SQL Server uses an index allocation map to list the extents used by a table or index, and the database engine can read that map for all the disk addresses to be read. So this allows the storage engine to optimize the I/O and large sequential reads. That being said, at the same time, it's kind of an anti-pattern to have scans, especially for queries that are looking for a single record. SQL Server also reads indexes a little bit differently. So it reads indexes serially in the order of the key. So the key is the leading column of an index, and that's typically the order of the index, and that's how SQL Server is going to read those pages. Some other issues we see are heavy scan workloads that are typical of data warehouses. Another pattern is Tempdb spills. So we haven't talked much about Tempdb. We've mainly been talking about internals of SQL Server, but the easiest way to think of Tempdb in SQL Server, if you're not super familiar with SQL, is that it's the page file for SQL Server. So when SQL Server runs a query, one of the things the query optimizer does is specify the amount of memory that's needed to complete that query. So things like join operations, sort operations, those are all going to ideally take place in memory because it's much faster than doing it on disk. However, if SQL Server has bad information about the amount of records in a query, and there are several conditions that can trigger this, like table variables prior to SQL Server 2019 had a fixed value. So SQL Server always assumed they had one row. That meant you could allocate too much or not enough memory, and your query would effectively page, or what we call on SQL Server, spill to Tempdb. And that's, once again, we've talked about how disk is orders of magnitude slower, so you're writing to Tempdb as opposed to just doing something that will happen really quickly in memory. The other thing Tempdb can be heavily used for is there are certain isolation levels which allow more concurrency, like read committed snapshot isolation. If you're using read committed snapshot isolation, each time a user queries, a version of the rows they're querying get written to Tempdb, and they're stored there. So Tempdb is a really busy database on a heavily used SQL Server, and its random more random write activity than it is random read, but it does have some degree of random read. So it's important to put that on a fast drive, and we'll talk about how that works in Azure and options you have. The other thing you should note is throughput for both backups and data warehouse workloads. Backups we address a little bit differently in Azure, and we'll talk through that in a couple of slides. So to identify IO issues on SQL Server VMs, the first step I always like to look at is if we think we have an IO issue, is to look at the SQL Server error log. So the error log will record if any occurrences of an IO take more than 15 seconds to complete. That one's a little bit problematic. If you see those, you probably either have a major storage or major indexing problem, or some combination of the two. It's rare that I see SQL Server with a storage problem that can't be at least somewhat remedied by indexes. And since we're in Azure, it's easier to build new infrastructure. Sometimes if you don't own the code, you just have to build really fast infrastructure. But if you can change things like indexes, always try to do that. You never want to go blame the storage team before you have a better understanding of what your database is trying to do, because about 80 to 90% of the time it is a code problem. There are times when storage performs poorly, and it's helpful to understand that. And the way you kind of do that, there's also DMVs we can look at in SQL Server. And when we do the demo, I kind of have a longish demo planned here for the end of this. We'll walk through the DMV that shows you latency by data file. But I like to look at SQL Server first. Then I like to look at Windows perfmon. So the two metrics I like to see are disk seconds per read and disk seconds per write, and those are pretty much what they sound like. It's how long Windows takes to complete an IO, and also disk bytes per second to tell me how much IO it's trying to do. There are some similar metrics on Linux. If you're running SQL Server on Linux, you can use IOstat. And then finally, I like to look at the VM platform or SAN metrics. So obviously in Azure, we're not using SAN, but you do want to look at, and this is an important dimension that we'll talk about here in a second, that each VM has a certain amount of storage bandwidth and storage IOPS that are associated with it. IO meaning IO operation per second. So that's effectively that disk writes per second or disk reads per second from Windows. And because of that association, you will hit throttling as you hit the upper limit of your VM. So it's important to kind of understand that. And that's really part of the platform. So Azure Storage has a pretty long history. It's one of the foundational services. Obviously, you can't really build a cloud platform with that storage, and it's really evolved over time. So when we started with virtual machines, we had this notion of a storage account, which you may still be familiar with, because we have those. And we still use those for things like blob storage, which we would use for backup. What you did when you created a VM was you created a VHD file in your storage account, and this fundamentally hasn't changed. And you would stripe multiple VHDs together to try to increase your performance and throughput, which was one way we did things. At the beginning, everything was hard drives and no SSDs, so that wasn't super fast. And then we got premium storage, and premium storage first came in storage accounts. And then we got what's known as managed disk. Azure Storage, like if you create an Azure Storage account, you'll notice there are a lot of options. You can create files, you can create blobs. Managed disk is a little bit different, is that it's not really part of Azure Storage, your storage account, but that's fine. We also have queues and tables. We're not going to focus on queues, tables, or really files today. We're going to focus mainly on blobs and disk, and I'll talk through. The queues and tables are just kind of programmatic things that you would use if you're writing a custom application. It's not something we're going to have SQL Server use. I left off file storage for the sake of time. You can use Azure File Storage in conjunction with SQL Server. The one scenario where you would really do that is if you're using Azure, a failover cluster instance of SQL Server, which was a shared storage architecture. That was That was the only native way to do that until quite recently. You could use Storage Spaces Direct to do that natively, but the performance was quite poor. Now Microsoft has the notion of shared managed disk. It's not fully featured yet, but so if you're building that architecture, that is an option for you. But the main two things we use with SQL Server, components of Azure Storage, are blobs and disk. Blobs are what we would use for backup. SQL Server 2012 and higher, if you're on a specific patch level of 2012, I believe it's Service Pack 1 CU2, you can back up your database directly to URL natively, which means you're backing up to blob storage directly. And this had some limitations until SQL 2016. Your backup file can only be 1 terabyte in size. Now with SQL 2016 and up, your backups can be up to 12.4 terabytes, which the 1 terabyte thing probably covered about 80% of databases. 12.4 terabytes covers about 98% of the databases I've worked with can fit into that model. If you don't have a database that, or if you have databases larger than that, you can back up to a file share, you can back up to a file server. There are other approaches you can take, but blob storage is something we're really only going to use for backups because the performance is not going to be what we want. And then disk storage is effectively VM storage. It's the better way of saying that is MSVM storage, but I don't make up names, product names at Microsoft. So within Azure Disk, we have 4 categories of disk. We have standard HDD. That's kind of the old school spinning disk. There's a lot of density and volume there. These are best used for things like backups or things that are infrequently accessed. So if you had a file server that had many petabytes of data and you didn't want to have to, and the data was infrequently accessed, you're mainly storing it for archival purposes, that would be the scenario where you use a standard hard drive. Standard SSD sounds promising, and it's a lot cheaper than premium SSD, but the performance is more analogous to the standard hard drive. The difference being the standard hard drive doesn't have a guaranteed performance SLA, and the standard SSD does. They're pretty similar. I think they do up to about 6,000 IOPS. The differences don't really come in IOPS performance until you get to very large standard SSD volumes. So if you're on like this kind of standard 1 terabyte or lower data volumes, you're not going to see a great performance improvement from standard SSD to standard HDD. I had a customer who tried to run their QA database servers on standard SSD, and we rather quickly gave up because the latencies were exceedingly high under volume. And we'll demo. I didn't build out standard SSD, but I built out a pool of standard HDD just so we could test to compare. I also built out premium SSD, which is premium SSD drives go up to, I believe, 20,000 IOPS per drive. They come in a bunch of sizes. And one thing you should note, and this is gonna just step away from like Microsoft marketing stuff, you'll note that if you buy a 1 terabyte premium SSD, it has 5,000 IOPS and obviously 1 terabyte of storage. And it's roughly, don't quote me on the price exactly, but it's roughly $135 US a month. If you buy a 2 terabyte, it's roughly $270 a month, and it's 2 terabytes, so you have twice the volume, but you only have 7,500 IOPS. And as you go in very large volume, you can go up to 20,000. But like the 4 terabyte drive also is roughly 4 times the cost of the 1 terabyte, and it only has 7,500 IOPS, so 25% more. So what that implies to me, well, it doesn't imply, this is how I build stuff. I build my storage volumes out of those 1 terabyte volumes because I can get more IOPS when I stripe across them, because that's one of the things we'll do, and we'll walk through this in a demo to show you how that happens. So a couple of things. Each virtual machine has an IOPS and throughput limit. As you approach that IOPS and throughput limit, your workloads will be throttled. So you'll see a tail off in performance. You can allocate more IOPS of storage performance than the VM has, there's no benefit to doing so. You won't top that. Each VM has a limit on the number of disks allocated to each VM, and this might be the one scenario where you want to use those bigger disks, right? Because larger volumes, if you have a very large database that's infrequently used, so the performance is less important, you might strike together a couple of 4 terabyte drives to try to deliver performance. So that's just a thing to note when you're building your architecture. You're choosing the right VM size is a component of your IO performance, as is the memory that's associated with that VM, because that memory is going to help you reduce the number of physical IOs you're actually going to have to do. And then each VM comes with a locally attached temporary drive, which is mounted as D in Windows VMs. It's mounted as dev SDV1 in Windows. And in most VMs, and pretty much any VM you would run SQL Server in, that's a locally attached SSD drive, which means it's a lot cheaper to go to that drive than it is to go to the network storage. You'll note I say temporary. So what does that mean? When your VM is deallocated or has a failure or anything like that, all the data on that drive is erased. However, which makes it not a great idea for a SQL Server. However, we do have the option of placing Tempdb on that drive, because you know what? SQL Server doesn't retain the data that's in Tempdb. It's recreated upon startup. So we can do that pretty easily. So that's a good benefit. And the performance of that drive is quite good, as we'll see in a few minutes. So some other best practices, Microsoft recommends using premium storage for data and log files. Microsoft also recommends that if you need, near sub-millisecond latency, you should use UltraDisk. I'll talk about UltraDisk in a second. I typically, even for mission critical systems, I like to use a mix of UltraDisk and premium storage, and it's mainly, that's for cost effectiveness. But not everything benefits perfectly from UltraDisk, as we'll see in this demo. You should separate log and data volumes, because one of the things you have with SQL Server is an option to cache your, with premium disk and standard disk, you can put a read cache or a read write cache on those disks. SQL Server does not benefit from a read-write cache because it will bypass the write cache, but the read cache can give you some benefits, as we see on the other bullet down. So using read caching on those data file volumes is good. We also want to stripe volumes across multiple disks using storage spaces, and that's kind of how we do this. You can let Microsoft do it for you if you're building from a SQL Server VM, and we'll walk through that too in a second. You should also use the temporary volume for Tempdb. Once again, if you're building a SQL Server VM template, Microsoft will do this for you. If you're not, you can create a scheduled task that will create a directory on that volume every time your VM starts, and then start SQL Server. The next one I agree with, but I know it's a lot more difficult to implement. Using data compression in SQL Server will always give you IO benefits. You're trading some IO for CPU cycles, but especially in the cloud where storage might not be quite as fast as if you're on premises and you have a really powerful array, like an all-flash array, you'll see a lot of benefits from compression. Of course, it's something you have to implement within your database, so that's a little bit harder. Microsoft also recommends you enable instant file initialization. So this is something that you used to have to grant a permission to your service account owner. Now in SQL Server 2016 and higher, you can simply check a box at installation time. All right, so let's walk through this demo I have here. This is pretty cool, and you'll get to see a lot of things. Let me zoom in a little bit here. The first thing I wanted to show you is just a page from Docs, and this is a class of VM that's become kind of quite popular with big database servers. You'll note this is the MSeries, so these are high memory VMs, and some of these go quite big. But you'll notice we have a size, the number of vCPUs, the amount of RAM these have, temp storage or SSD, so that's the SSD I was mentioning. So here we see 2 terabytes, the max number of data disks, which is 64, the maximum IOPS, which is 80,000 here, and that's cached, and then the max uncached IOPS is 40,000. So you can see the impact that cache makes. It gives us basically double the amount of IOPS. One other thing to note, this is a little bit of an aside here, you'll notice some of these VMs, and this is emblematic of all of Azure, the amount of RAM you have available to you correlates directly to the number of CPUs you have available to you. And of course, that's the way servers are built because Microsoft has to plan that way. Unfortunately, SQL Server is licensed by the CPU core, and that can be quite expensive in terms of licensing because SQL Server licenses cost roughly $7,000 a core. So if you need 1.8 terabytes of memory, but you don't need 64 cores of CPU, Microsoft does offer an option to let you do constrained core VMs. A constrained core VM is they're giving you the same VM and they're just not letting you use all of the CPUs. The Azure compute cost of that are the same, but you don't have to license those cores for SQL Server, which makes it a very promising option. The next thing I wanted to showcase, and this is a new VM, and this is how I started out building the VM that we're actually sitting on right now. You're in the VM where I'm to show you stuff. If you build a new SQL Server VM, Microsoft will configure this for you, or give you the option to configure it. And this is only if you're using the SQL Server template. So if you're building a standard Windows VM and installing SQL, you won't see this. But here, if I say, let's increase the number of disks to 8, I can then, I can see my IOPS change. So here, I can choose my disk type. They don't have this wired up for Ultra yet. By default, they use the 1024. They will also configure the caching for you. And they'll put your separate log. They'll also add Tempdb to the D drive. And I haven't, typically I build this myself, so I haven't actually checked this out. So I'm presuming as part of the build in your VM, let's go to the library here. Actually, I don't see a scheduled task, so I don't know how they're creating the volume when you fail, but it's there. So if I look at my disk, sorry about that. If I look at that disk, I see Tempdb is there, and indeed Tempdb. So remember, this is part of the SQL Server configuration options. The nice thing about this is you don't have to do anything in Windows after the fact. It does everything for you. And then here, I wanted to show you the VM that we're running on today. So I've had some workload going through it, and I have a number of disks configured. I did not use the SQL Server template. I built, never mind. I built my own. That's why Tempdb is, there is no scheduled task. Couple of things to note. You'll notice I have a 2 gigabyte pool for premium, or 2 disks allocated for premium storage, 2 disks allocated for standard storage. I only have 1 for Ultra disks. This is a little bit interesting. So Ultra disk is a little bit more configurable in that the number of IOPS associated with your Ultra disk and the amount of throughput it has are configurable. We can even update them on the fly. So here I'm going to update this throughput number to 1024. And by the way, you'll note my billing changes. That's why I kind of had it low. So even though I can update that on the fly, and while we're here, I'll update IOPS to 10,000 because I'm going to delete this resource group pretty soon after. Now I'm starting to get billed for that. So Ultra disk costs have 3 dimensions. It's based on the volume of data you have, the size of the number of IOPS you have, and the bandwidth you have. So that's kind of an interesting scenario. I was a little bit intentionally throttling myself earlier. I did some baseline workload testing, but let's go take a look at that. So here, I'm using a tool from Microsoft called Disk Feed. And just so to give you a point of reference, I have a few volumes on this. Like as you saw, I have premium storage, I have ultra disk, and I have standard, and they're labeled with the first letter. So U is my ultra disk. Let's do a quick, this will be a quick test. It'll be 20 seconds. And while that's running, I want to show you just what we do to pull our storage to get those IOPS. So here we're in Server Manager in Windows Server. And we have two pools. One's called Premium Pool and the other's called Standard Storage, because I wasn't real good about consistently naming stuff. But I can see that I have 2 disks in each pool, and then those disks make up a virtual disk. One of the interesting things about the way you stripe in Azure is that you don't use any sort of RAID. So when you configure this, you get the option if you want to use simple, mirror, or parity. And simple is what you want, because the Azure infrastructure provides the RAID for you. Behind the scenes, there are 3 copies of each of your disks. One of the differences here between UltraDisk and Premium is because UltraDisk, the IOPS aren't tied to the size of the disk, we don't have to do this. The reason why we have to do this in Premium and Standard Storage is that the IOPS are tied to the size of the disk. Microsoft has recently introduced some changes to that, like where they've reduced the amount of, there are smaller disks that have higher IOPS, but for the time being, that's kind of what we have to do on Premium Storage. So my workload test completed. In here, if we look at what it ran, just let's zoom back up a little bit. So here I said at 8K block size, duration of 20 seconds, write percentage of 25% to a 20 gig file, write and give me the feedback. And so here my total IOPS were 6,500 at an average latency of 4.9 milliseconds. So that's pretty good. It's not exactly the sub-millisecond latency that Microsoft promises. And I haven't been able to consistently see that with UltraDisk. But here I see my minimum latency was 0.46. My 50th percentile was sub-millisecond. My 75th was 1 millisecond, but my average wasn't so good because I had all these really high edge. And that's kind of indicative of my IOs getting throttled by the VM. So here, if I run the same test against Premium Storage, you're going to see relatively similar numbers. And this is why I'm saying don't just go all in and buy UltraDisk until you need to get there. It's not necessarily the case that you need that. And we'll run that workload, and then we'll do a quick look at HammerDB because it's something I like to show as well. And for the sake of time, I'm going to skip over standard, but I've run a lot of workload on standard, so you'll see. So here you see our IOPS are quite similar, and actually our average latency is lower. And I think that's mainly affected by the fact that we have read caching enabled on these premium disks. So lately in my testing, I haven't seen a scenario where I've seen a benefit of going to UltraDisk for data files. I have seen it benefit transaction log files, and I have seen it benefit Tempdb files. But just to give you a little bit more of a point of reference about the temporary drive, I think actually I did a clear, so I don't have that. I did a test, the same test we're doing here on the temp drive, and the numbers are even better. The latency numbers are much lower. You'll see higher IOPS numbers. So for Tempdb, a busy workload like that, that's going to be a good way to go. Let's take a quick look at HammerDB, and we'll change this to Ultra. And if you haven't used HammerDB before, it's a little bit more realistic of a test. And so the tool we're using here is Disk Feed, and all that does is synthetic IO. So there's no CPU load involved. Here, what I'm going to do is run a workload. So now we're running a workload against our UltraDisk. And more importantly, we can see our transaction counter. And this is going to refresh every 10 seconds. So here we see We're going to go 27,984. This will probably peak out at about 45,000 or so IOPS. Yeah, 45,000. And since we're a little short on time and I'd like to take a couple of questions, I'm going to go ahead and kill this. We see 46, and then I'm going to change over to my premium database. And I know I didn't run that long enough for a true performance test, but you'll get the idea, and trust me, the numbers don't change that much. So here, if we go to premium, we also start out at 12 transactions per minute, and we see 36, so we're a little bit lower, and we'll give it a couple of cycles to run. $44, so we're actually pretty close to what we were seeing on UltraDisk. Let's give it one more 10-second refresh before I kill that. 45, so very close to what we see on UltraDisk. So if we go over to Management Studio, I have a query up, and this is a query I really like. It's from a friend of mine who's an MVP named Glenn Berry. He worked for SQL Skills for a long time, and this is part of his script repository. And it will report our average latency per database file. So here I'm going to go ahead and rerun this query. I've been doing work all morning on this VM to get rough estimates of what our performance looks like. And you'll notice here, our premium data file, our MDF, has an average write latency of 12.7 milliseconds and an average read latency of 3.2. Transaction log is kind of similar, 3.1 write latency, 4.2 read. Those are pretty good numbers. Those are very good, especially this isn't a huge VM. This is like a 4-core 16 gig VM. Standard, on the other hand, not so good. 252 milliseconds of write latency, 2.6 milliseconds of read, which I mainly attribute to the fact that there wasn't a lot of read activity going on in this TPCC benchmark. It's mostly writing. Then if I look at my UltraDisk, I see 14.8. So very, very similar numbers to the premium. However, the write latency to the log is lower. UltraDisk currently doesn't support caching, and I mainly attribute that performance difference to that. So what I've been doing for my mission critical workloads is putting them on UltraDisk, but just the transaction logs to save costs. So I try to isolate the number of IOPS the transaction logs are doing, and once I get that isolation down, then you can size that UltraDisk accordingly, which makes it slightly more cost effective. But in general, you'll see if you configure premium storage and you can configure your workload appropriately, you'll get all the performance you need out of Azure Premium. So SQL Server is heavily dependent on storage performance. It's something to be aware of. You need to be aware of your VM storage capacity, both from a performance and from a number of disk perspective, and then follow the best practices for Azure Storage that the SQL Server team applies. I think that's a real best practice guideline. I've tested a lot of their best practices, and I didn't always agree with them, but I think I mostly do now. There's just about everything they recommend that I agree with. And do we have any questions, Michelle? Or you can type your questions in the chat and I can see them. Yeah, so if anybody has any questions, just type them into chat. I had a question on what's the best way to learn SQL performance assessing tools, and it's kind of a complicated answer because SQL Server performance is so multifaceted. The training, I'm actually in the process of building some training materials for Microsoft for one of their new learning modules for databases, and I was just writing about all this stuff. There's a lot to grasp. I'm trying to think of any books that I have. It's so multifaceted. It's really the fundamental basis of SQL performance comes down to query execution and how your queries are running. So I think anything you can read about query optimization. Redgate has a free book on query execution plans by Grant Fritchie that's pretty good, and that talks a lot about the way the optimizer works. And in terms of the tools that are available in the space, all the tool vendors have pretty similar offerings. I've worked with all of them, so full disclosure. I don't really have any preferences. I would check them all out. My preferences tend to be, I like to gather data from the database using scripts like I just showed you guys. The other thing that you should be aware of is that Microsoft in 2016 introduced the query store to SQL Server, and that gives you a lot of valuable data around that. But it's really helpful to understand how query execution works, and that's really going to be what drives the performance of your servers. Any other questions? Well, thank you, everybody. Have a good rest of your day or night, and I hope you enjoyed this.
Thank you.
Thanks.
Thank you.
Bye.